Welcome to the next session, everyone, and please be introduced to Wabe Koelmans, who is the CTO and co-founder at Exaddon. And today Wabe will tell us about microscale metal 3D printing. Slides look good, sound is good, camera is good. Off you go, the stage is yours.
Thank you very much, Christoph. Yes, indeed, my name is Wabe. I work at Exaddon, and at Exaddon we do metal 3D printing, but it's a bit special. It's really at the micro scale. So if you look at an overview of all these type of micro additive manufacturing technologies that are out there, this is an overview made in 2021. You can see that we're really on the smaller end of the length scales. So there's ceramics, there's glass. Let me turn on the laser. There's polymers and there's metals. And in metals, really, Exaddon is here, and A is at the smaller end of the length scale, starting at about a micrometer of object size or resolution, if you want to. So, as a main product, Exaddon has a system that's called Ceres. It's a complete standalone system. It's a system that's built for research. It's really a scientific instrument that allows you to print metals at the micrometer scale. And it's really a specialized instrument. So that comes with nano positioning stages. It comes with a very accurate microfluidics control system to dispense the liquid needed for the printing, and also computers. So it's a complete system that we provide there. So at the heart of this system, there's a nozzle that does the 3D printing. This nozzle is a derivative of an atomic force microscopy cantilever. So it's silicon-based technology. This is the cantilever, but it has a channel inside. The channel is there to deliver the liquid to the aperture. So instead of having a tip like in AFM, here there's a small hole at the end of the cantilever that delivers a liquid to the place where it needs to be. In this case, we deliver an electrolyte to do printing. So if you look at this schematic, you see the liquid comes from this reservoir inside this plastic adapter, and there's a tube connected at the back, and with air pressure, the liquid is then pushed into this channel and out of the tip. And because this tip is very small, the aperture is only about 300 nanometers in diameter, we go to really low flow rates. A picoliter per second is typical. You can even go into the hundreds of femtoliters at very low pressures. So in real life, an adapter looks like this. So this is where a silicon cantilever is glued on, and this is the consumable of the instrument. This is the tip that you fill with an electrolyte. Here at the back, there's a small reservoir where it holds a whole microliter with which you can print for many hours. And under the electron microscope, you can get a sense of the scale of things. Zoom in. Yeah, it's an entirely different world where you can print for 40 hours with only a microliter of liquid. So the process itself works by good old-fashioned electroplating. So really the trick that we're playing is that we limit the electroplating to a very small region. So we call it local electroplating. And we do that by working in a electrolytic bath that's deprived of the metal ions. So there's a typical electrolytic cell with 3 electrodes, but there are no metal ions in the bath. So as soon as the potential is applied between counter and working, there is no deposition going on. So only if the printing nozzle comes very close to this working electrode and ejects some copper ions, there can be deposition ongoing. So this very close, in the order of a few micrometers distance. Otherwise, the nozzle is too far away